would be discrete choice models, and those are quite after that. So we have both of these lectures and then that one. So
no,
this
is say day 2.
Yep.
So basically lecture you will be.
We could just end with that lecture.
Yeah.
Okay.
You can. No,
Okay.
But yeah, like today we can end with that
Yes.
lecture, and that can be from 4 to 6.
Okay. So all right. So the way we'll do it, that's fine. So the way we will do it today is we'll have a very short lecture to begin with, talking about some general properties again of models, and we'll go through that fairly quickly. And then we're going to go into count models. Okay. So and then we'll have 2 tutorials back to back, and then we will take the break. We'll finish this morning section. And then we will, in the afternoon, begin our first lecture in the discrete outcome models. Just as an overview, how many people have been exposed to discrete choice models before? Anyone has been exposed? So about half of you. Okay, so discrete, just so you know, the discrete choice models are the hardest models that we'll talk about, most difficult. Bayesian ones are a little bit difficult too, but the discrete choice are the most difficult, so we're plunging right in. But because of that, the lecture around those models will take a little bit more time. So that's where we are. Before we dive in today, are there any questions lingering from yesterday about LIMDEP or about regression or about anything that you thought of overnight and you went, oh my gosh, what was he saying when he said this in class? What did he mean by that? And that does happen. When you digest this material, you all of a sudden relook at it, or you look at the notes and you go, oh my gosh, that made sense when he said it, but it doesn't make sense anymore. So any questions, lingering questions from yesterday that that you feel like you have to have answered before we plunge into today? Anyone? You're all pretty comfortable with what we did yesterday? Okay. All of you, yes?
Suppose if you take on the observation on a Likert scale.
Yes.
Is there any chance that we can convert this Likert scale with an interval scale?
The question is, can you convert a Likert scale to an interval scale? Good question. I've never been asked that question before. My hunch and intuition would say that no, there is no way to convert it. So the one thing about data is usually the information content that what we have in raw data cannot be improved. It can only be reduced. So a Likert scale would be an ordinal variable. And so taking it to a ratio scale variable would imply that you're going to add more information. And we don't have more information to add. So we can't go up the scale, but we can go down the scale. In some cases, we can go down the scale. So, for example, you could take a nominal scale variable with 5 categories and break them into 2 categories. It's got less information. You could take an ordinal variable like a Likert scale and say people that answered above this and below this, and it becomes nominal, just 0 or 1 above a threshold or below a threshold. So you can go down the scale, but I'm not aware of any techniques of going up the scale of information, content. Okay, yes?
On the same line, I have a question on the Likert scale. Is it right to take an average of Likert scale and then say the average answer is this one?
Yeah, you can certainly say the question, can you say compute an average on the statistic? Yes, you can say the average score on this question with a Likert scale response was 3.5. The thing, but because it's an ordinal variable, you have to know that 3.5 is how it's derived and what it means. You know, it's the breaks between categories in that scale are different for different people, and so a 3.5 has a different meaning there than if it's a 3.5 average number of cars in a queue, right? But yeah, you can. Any other questions before we get going today? All questions are good questions, so no such thing as a bad question. All right, so this section is going to be fairly short, but I'm going to go into a little bit of detail around, just a little bit, not a lot, but around why we need to get the models right. So remember in the tutorial yesterday, we spent some time trying the different regression models. And remember, I tried to trap you, and I trapped a number of you, and it was an easy trap, and always I set you up because you wouldn't have known, most of you wouldn't have known to not do that, but it was intentional to say, well, what happens when the model is specified incorrectly? So specification is this notion that we're trying to capture with our model the real relationships that are happening in reality. That the real relationships that have generated the data are unknown to us. And we're trying to specify a model that as closely resembles that real data generating process. And when we do it wrong, there are consequences. And so what we're going to talk about here is what are those consequences very quickly about when we do it wrong. I don't have the, here we go. Why is it? It's not doing anything. Does that have a power button? Wow, it's just frozen now. Okay, so we're just going to go through some of the assumptions and what happens, what these assumptions mean. And if you remember, so what we talked about is blue. You should remember what blue means. Best linear unbiased estimator, right? So, and that's true only when you meet the assumptions of the regression. And so if you don't, then your parameter estimates are not reliable predictors or not a reliable reflection of the underlying model. So, thank you. So what we have here, if we flash to the PowerPoint. Okay. So if you remember this, so I wrote out some assumptions and really talked about them generally, so we'll just go into a little more detail. So there was a normality assumption, right? The disturbance term is approximately normally distributed. It only needs to be approximately normally distributed. And it turns out that that works a lot of the time. Sometimes, so my experience is, and my advice to you is that when it doesn't work, it doesn't work miserably. In other words, when it's not normal, it's really grossly non-normal, and you can tell. So it's usually a very skewed distribution when it doesn't work. We also have A2, which is the expected value of the error terms is 0. We had a homoscedasticity assumption, that the variance is constant. We had serial independence assumption, that is, the error terms are not distributed across space or time. So you can get correlation in both instances. So if we measure at different places, say in geographic spaces, we can get the error terms that are, for example, on adjacent spatial measurements to be correlated. we can also have that kind of correlation that goes across time. Both would be, the serial independence refers to the time dimension, but you could have spatial independence, and that's expected as well. You just don't want to have any correlation between the error terms. Let me ask you this. So I made a statement. So if I said if we measured two things in space, let's say, for example, we had states or provinces or cities. Let's say cities, adjacent cities, and I measure something in those cities. Let's say we measure population growth. And you had a model that was predicting population growth across two cities. My question to you is, why do you think we could have the error terms in the model for those two adjacent cities? How could they be correlated with one another? How would that happen? What's happening there if a model predicting population growth as a function of some x's would have error terms, two adjacent cities where the error terms are correlated, where we violate this E sub I, E sub epsilon sub j is not, the correlation is not equal to 0. Yes?
There are some spatial effects, spatial dependence.
Yes. But you're absolutely right, but I want you to be more specific. What do you mean spatial dependence? What does that mean? Exactly.
Things which are more close to each other, they are more related to each other. The basic geography of, are you connected?
Okay, you're right. I actually think so. You're completely right, but we can be more specific. And I think the spatial dependence thing is a very, very interesting discussion topic. But what it is, you're absolutely right, but I'm going to go into a little more detail. What it means is that there's something about those spaces being adjacent that they share, because they're close to each other, they share a lot of things. They might share topography, they might share weather, because the border we put as humans doesn't necessarily follow, right? So that what it is that because they're close, they share unobserved x's. And for them to be correlated, those x's would have to be related to the outcome. If those x's are irrelevant to the outcome, then the correlation would be 0. But if those x's happen to have even minor second-order effect or primary effect influences on the outcome, on population growth, then, and you don't include them in the model, then they're shared unobserved effects. That's typically how correlation like that happens, is that we've omitted things in the model. They may be second-order effects. Remember that discussion about first order versus second order. It may be minor effects, but they're still effects nonetheless. And so if you leave them out of the model, they show up there. And that's a problem. That's what that says. If we do that, and that can happen spatially and over time. Non-stochastic x. This is the thing we discussed a little bit yesterday, that it's not random and has fixed values and repeated samples. So let's talk about what happens when we don't do these things, and these things are making it tough for us. And I have to say, a lot of statisticians, sort of entry-level statisticians and modelers, ignore all this stuff. And they mess up their models because they're not aware of these kinds of things. Okay, so it's really important that we're aware of these. Okay, so omitted variables. This is a specification problem. I didn't list this as one of the assumptions. Omitted variable, so it is an assumption, but it shows up. The assumption is that we're correctly specifying the model, the true underlying model. And if one of the errors we can make is omitting variables that are important. So the way that works is, you can see here, and I'll just walk you through one. So if the true model, the unknown true model, is beta 1 times x1 plus beta 2 times x2, right? That's the truth. That's the real process that generates the data. But we estimate a model, yi equals beta 2 x2i. So we omit, we fail to include beta x1, the effect of x1. The effect of x1 is beta 1, right? So we fail to include x1. So what happens, and it can be shown, and this is in my book, but what it shows, and you can show, and this is an important, and this is a generalizable equation, that the estimate of beta 2, that's the variable you included in the model, is actually a function, is actually the true beta 2 plus some fraction of the effect of beta 1. That fraction is the fraction of the covariance of x2 and x1 divided by the variance of x1. So it's some fractional, so it's 0.1, 0.01, 0.05, 0.9. So essentially what you've got is your beta 2 subsumes the effect, a partial component of the effect of beta 1, or x1. And if you look at the equation, the more related, higher the correlation between x2 and x1, the more biased that estimator is. So if the covariance was 0, the covariance between x1 and x2 is 0, then that term goes away, and you have no effect. And so now we're getting to the details. And so if you remember yesterday, I talked about, well, experiments are better than observational studies and things like that. Well, here is one of the reasons. In observational studies, we're stuck with the covariance between variables. So someone asked me in the modeling yesterday, or after class, what's a critically high covariance or correlation? Not covariance, but correlation. So they're related by a square root. And we talked about values greater than 0.7. Well, that's pretty high correlation. So if you have something about 0.5, then all of a sudden we are getting, and if we omit something that's correlated, that's important, then all of a sudden we are going to have bias estimates. But if we have an experiment, in experiments we have the luxury to make sure, and we haven't talked about this yet, but one of the things about experiments is we can design the experiment such that the covariance between x's is 0. That's exactly what experimental design is. The whole science of experimental design is about how to design experiments so those covariances are 0. Okay, so a couple things to note here is that the correlation that we observe in observational data is problematic for us in modeling in general, but it's really problematic when we start thinking about omitting variables that are important and those kinds of things. So now let's take the reverse case. Let's suppose that the true model is beta 2 x2 plus epsilon, but we estimate a model incorrectly that includes x3. Okay, x3 does not, in truth, influence x or the outcome, but we've included it, so it's irrelevant. So the irrelevant variable basically means that we're omitting the information that is actually the effect of beta 3 is 0. We're ignoring that information. So in general, not accounting for all of that information leads to loss of efficiency. What was efficiency? The variance of, or the standard errors of the estimates, but no loss of consistency or bias. So what's the difference between efficiency and consistency, if you remember that? Efficient is a small sample property. Consistent is a large sample property. So and we talked about that yesterday. So here what we're saying is that this really is a problem for small samples. They're not efficient, so small samples are going to have large standard errors. But as the sample sizes get larger, that problem goes away for us. So there's kind of a glimpse of how the statistics differ depending if you have small sample or large sample. And there's no bias from this. Okay, so there's no bias effect like there was of omitting important variables. But we have loss of efficiency. So, so oftentimes one of the criticisms I level against people that put in papers in journals and stuff, and they put their final model includes a bunch of irrelevant variables. We have to know that that isn't eroding the efficiency of all the ones that are important. And it's also including variables in the model that we know aren't important. Okay. And so anyway, so in that case, beta 2 that we've estimated is unbiased and consistent, but is not efficient since the variance of beta 2 star is greater than the variance of beta 2. The exception is when the covariance is equal to 0. Then estimators are blue. So again, not a problem if it's an experiment. You can leave irrelevant variables in the model. But most of the time, we don't have experiments. And we have observational data that do have correlations. So nonlinearities. So let's say we estimate a model y equals beta 2 x2 plus epsilon. But the true model contains squared terms. So that actually should be, I think there's a mistake in that. So it should be beta 2 x2 plus beta 3 x2 squared plus beta 4 x2 cubed. Okay? Because we wouldn't have the same term twice. And if that was a true model, but we only estimate, this is just finicky. That one, we have the same problem. All right? We have inconsistencies, and we have biased and inconsistent parameter estimates. So it's really important for us to try to get the model specified as accurately as we can. And again, my comment from yesterday was, well, if you start with an understanding of what you should be getting, it's a much better starting point than just playing with data and trying a bunch of different things. Non-zero disturbance term, I'll go through quickly. This is rare. It doesn't happen a lot in practice, but it does create problems. The main thing to note here is that we generally want to include the intercept terms in the models. When we take them out, it causes all kinds of issues for us, and particularly with the expected value of the epsilons equals 0. Okay, errors in variables. When we measure things poorly, we can measure x's poorly or y's poorly, or say without great precision. And so if y is measured with error, then we use y star instead of y. So it's actually y star is the actual y plus some error term, u. Then depends on the covariance between u, I, and the x's. Whether you end up then with a biased or consistent estimator. So again, be aware of these sorts of things. This is also a much less common problem than, say, including irrelevant or omitting important variables from models. But it does happen. And I would suggest that in practice, if things are really poorly measured, we need to do some kind of corrective measure in the model to deal with that. Correlation between explanatory variables and disturbances. This one throws a lot of people. And they say, what if we have? This is the endogeneity problem. And it happens a lot. So what we did in tutorial yesterday happens in practice a lot. The point that I hope you left with yesterday in the lab tutorial session was that the statistics will give you great information when you include endogenous information. It's often not as blatant as it was yesterday. If you remember yesterday, we went from like 24% R squared up to 90. It's often not that abrupt. You might go from 24% to 34% by including an endogenous variable. And we just don't realize it if we're not thinking about what causes what. The only way, really, there are some endogeneity tests. There are some ways to test that statistically. We'll talk about those a little bit later. But the main way to determine this is just to know your data and know these causal questions. What influences things? And so the main question is, does everything on the right side of the equation not influenced by y? That's usually the error that happens the most. And how do you answer that question? You have to sort of, question that process and what happens, and know the data well enough to know what factors cross y. Now, it turns out this is a problem. I'm describing a problem, and it makes you think, oh gosh, well, we can't deal with it. We actually can deal with it. We can deal with endogeneity very, very well, but just not in linear regression. We have methods for dealing with endogeneity, but we have to recognize it and say, okay, we need to model this differently to account for these issues. Yeah. Yes, it's a different type of model. So we're going to talk about simultaneous equations. Estimation is one of our, and simultaneous equations is exactly a modeling procedure intended to deal with endogeneity. Okay, so we will deal with it, but we have to recognize it. And the problem is often people don't recognize it and model it and do not account for it. Let me give you an example just to cement it. Because one of my very early papers with with Do-Gyong, actually, we looked at a lot of people had been modeling crashes at intersections and in count models, which is what we're going to do next. And one of the X's that people were using in the count models for intersections was whether there was a left-turning lane. So this would be in North American driving on the right-hand side. So when you're coming to an intersection, there would be a separate left turn lane. So it was an indicator variable, okay, binary, 0, 1, whether or not there was a separate left turn lane at intersections for people to then navigate the left turn. That was one of the predictors. Seems innocent enough. Binary, not a problem. Well, it is a problem because those lanes are installed when crashes, typically, when crashes reach a certain threshold. So the engineers say, well, the intersection is humming along just fine. Oh, no, we had 4 crashes last year. That's more than 3, which is our allowable limit. So we're going to go in and put in a left turn bay to make it safer. All of a sudden, Y, which is the number of crashes, has been a direct influencer of X, whether or not there's a lane there. And that is endogeneity by definition. So we had to deal with that. And it turned out when we dealt with that and modeled that as endogenous, everything changed. The model was completely different. It gave a completely different sign of effect and was told a very different story than when you did it incorrectly and not treating it as endogenous. Okay. So selectivity bias is another issue, and this is about sampling. So if we recognize that what we're trying to model is that the individuals within our sample are self-selected, or there's some selection process that makes that sample biased, we call it selectivity bias. And we have to account for it and deal with it. And the example I used yesterday for selectivity bias was when, if you look at amount of sort of active travel, bicycle and walking, people living in very active travel friendly neighborhoods, they're self-selected to those locations. So it doesn't tell you if someone that didn't want to live in that location, how much they would walk and ride, because they were self-selected. And we have to account for that in the model and the setup. And we have ways to do that. Okay, so here's, and again, if you estimate a model on a self-selected sample, you're going to get biased estimates for the model that you're estimating. So normality, as I told you, that's usually gross non-normality when you see it. It's usually some highly skewed distribution, and we have to deal with it. But often, if it's in a cluster in the middle and cloudy in the middle and sort of has two tails and some symmetry, it's usually good enough by the Gauss-Markov theorem, central limit theorem. And so that these are obvious. But when it is not approximately normal, and we do run into cases, we need to typically do a transform. The first course of action is to transform the scale of a variable. We haven't talked about transforms at all yet. So if you think of it this way, the data that we collect is somewhat arbitrary in the scale. So if we measure distance in meters, the meters part is, there are an infinite number of ways to measure distance. And it turns out we got meters. But it could have been kilometers, it could have been feet, it could have been inches, any number of dimensions. And likewise, you could take the log of meters and the square of meters, and you can change the scale of data very easily, and it doesn't change the information content whatsoever. Right? If you have data measured on meters and you put them in kilometers, or if you take them in squares, the information content has not changed. So there's nothing that prevents us from taking data and changing the scale to meet requirements of a model. Okay, so we do that. And in the book, there's an appendix that talks about a whole bunch of transformations that are useful to help us in modeling. So one of the transformations we would do is transform y, the scale of y, to meet normality assumption. And it's perfectly legitimate as long as we remember that we transformed it and we transform back when we want to make predictions or use the model. And we can talk about that further if anyone's interested. Heteroscedasticity, that's the one where we have increasing variance. Again, that's typically a transformation. The only thing that will fix heteroscedasticity is a transformation on y. The other approach is to use different methods other than linear regression to deal with heteroscedasticity. There are models that are built for heteroscedastic situations. It does happen, and we typically need to deal with it. Although the consequences of heteroscedastic regression are not all as severe as some of the other things. So unequally sized observation units, so you have small cities and large cities and other things like that. So that can lead to heteroscedastic variance. Aggregation can lead to it. So a number of data processes that can lead to heteroscedastic results. And you can look at and diagnose this quite easily by plotting the residuals versus the independent variable and looking at plots of your error terms. So it's very easy to do in LIMDEP and all software packages. So you can very quickly assess heteroscedasticity. Okay, I think the last one we talk about is serial correlation. But again, it could be spatial correlation. It doesn't really matter. We just have these error terms that are correlated. We talked about how that happens. Over time, so the same process that happens over space is we have omitted variables that across space. But the same thing happens over time is usually we have the same thing that we omitted from the model at time 1 is also omitted from the model in time 2. And so we observe the same entity, so it still possesses the same attributes that might impact y as it did in the first time period. And we've then observed them again. And so epsilon in those cases contains, again, the unobserved shared effects across time rather than across space. And so there are ways, and there are whole methods built around serial. If it's serial correlation, about time series methods, we won't talk about time series models in the class. But it's in the book, and there are whole methods built around how to properly model data measured over time, deal with the serial correlation and those sorts of things. Okay, multicollinearity. This is when we have x's that are correlated together. And I had a long discussion with one of you yesterday, a couple of you actually, about correlation and how bad it is, and whether we should, or we're forced to take things out of the models. There are differences of opinion about it, but I think if you ask the leading econometricians and statisticians, they would tell you that it's not a problem under most normal circumstances. It might be a problem if they're super, super highly correlated, really high, like 0.8, 0.9. But the time when it's a problem, so let me explain why it's a problem and how it's a problem. It's not a problem to have two correlated variables in a model for forecasting, for explanation. So for forecasting, you're just forecasting future values. It would be a problem in forecasting if the correlation that exists at the time of the data collection no longer exists in the future or got worse in the future. So you have an x1 and 2 are correlated now, and you think when you're going to forecast 4, they would no longer be correlated, then it's a problem because they've had shared effect. In explaining things, so if you're using the model to explain a process, the problem is that they don't vary independently. So the interpretation, for example, of saying the marginal effect of x1 on y, that is, if you change x1 by a small amount, its impact on y is such. You can't actually say that with a straight face because you can't change x1 by itself. If you change x1, then because they're highly correlated with x2, you're actually going to change x2 as well. And the marginal effect on y is going to be also the change of x2 as well as the change of x1 because they're not independent. They're highly correlated. So, but if you manage those, there's no problem. And you don't have to take one out of the model if you think they both are important. Okay. A lot has been written about that, and you can read that in the literature. Yes?
For example, if you consider the multicollinearity and omitted variable together,
Yes.
so they are quite related, right? Because omitted variable, if we are omitting some variable which has high correlation with, and it is relevant, it is of course not irrelevant.
Yep.
And if we are omitting it, where it has high correlation with one of the included variable, then it's a problem.
Yes.
Then multicollinearity, like two variables which we think that very important, and we are omitting them, omitting one of them is also a problem.
Yes. Yes.
So, like, is there any, as you said, like if it is very, very high, like one can be explained with the other, then probably it is a problem to include both of them, right?
So it could. So let's say we had a 0.8 between an x1 and an x2. And I shared this yesterday. There are a couple things you can do. So one of the things you can do, and this goes into changing scale. So you can change the scale of one of them, or both of them. And so the way to change the scale is to calculate the mean of the variable and subtract the mean from everything. So take every bit of the variable and subtract its mean of that variable. And so now you have pluses and minuses for that. And you do the same thing for the other one, x1 and x2. And now usually the correlation will plummet. And so you've dealt with a correlation problem because you've changed the scale, but the information content is not lost. But the interpretation of the coefficients is now different. So it's not a unit increase in this. Now it's a deviation from the mean now. And so there are ways to deal with it, but to leave them in because you think they're important. And then if that doesn't work, then you can totally standardize it and divide it by its standard deviation. And then you have a standardized variable. Still haven't changed the scale, still haven't, or I mean, changed the information content at all, but you've dealt with the correlation. So those are techniques, and there's others in the literature talked about. Okay. So I think that does it. All right, any questions about that? So that was a fairly short lecture, just really about we need to get these models right. There are consequences if we don't. And so that's all we'll talk about that. Now the rest of the class is going to be talking about model-specific, different types of models. So I think we've covered enough of the general modeling, at least for what the intent of this course is. But you have a question.
Why is it important that there should be no correlation between the errors?
So the assumption, the question is, why is it important there's no correlation between the error terms? The assumption of the ordinary least squares estimation is exactly that. The theory that has developed statistical modeling says that in order for everything to work out well, for the parameters to not be biased, so those things that we talk about efficiency and bias that are important for us, those all rest on the assumption that the error terms are not correlated.
But will that be a problem if I'm trying to do, let's say, driving behavior in one part of the city and then in a completely different place, if I'm expecting the same behavior, shouldn't they be showing the same error?
Okay, so let me answer that in a roundabout way. When I say these are problems, they are problems for linear regression, which we've talked about so far. Almost all of these problems can be dealt with by going to different modeling techniques. So one of the reasons other modeling techniques have been developed is because they've said, well, we have this correlation problem. Often that's endogeneity that causes the correlation. But it's not. It could be spatial dependence, or it could be serial. So if it's spatial dependence that causes the correlation, then we start to include spatial effects to get rid of it. If we have serial correlation, we use time series methods to deal with it. If we have endogeneity that causes the correlation, we use simultaneous equations, estimation, or structural equation models to deal with it. So it's only a problem in the sense that it means you can't use this method. It doesn't mean that we can't model it. Okay, and that's the case with a lot of these things. Okay, any other questions? Yep.
Could you explain that case of two cities where the population growth is a variable, and if there is a correlation between these two, then there would be a problem in our model.
Yeah.
We would deal with it somehow. So can you again explain that how it would be a problem in our model?
Okay.
Secondary factor that you were talking about.
So, okay, yeah. So let's go back to the example of I've got a population growth model, and I've got two cities that are adjacent to each other. So essentially, so the argument is that essentially you've omitted variables that are important in population growth that are shared because these cities are next to each other. So these two cities might share it, but the city over here may not. But it actually could be that these two cities share it, and the ones that are a little bit further apart share less of it, and then over here they don't share it at all. You can imagine a case, weather, right? The further away we get, the less they share weather. Does weather affect population growth? If weather had no impact on population growth, then it doesn't matter. So it'd have to be a variable that would impact population growth. If that shows up, we know it's a violation, and it causes biased parameter estimates. So we can actually test it. So we could estimate our model, and we can look at a correlation, a spatial correlation, calculate a spatial correlation of the error terms of our model. And if it shows up to be non-zero, significantly non-zero, we could say, I've got a problem. A problem in the sense that I've got to deal with a problem, not that I can't now model this process. So I might take that same model and add spatial effects. So I might say, okay, I'm going to allow there to be a term in the model that picks up this correlation across space, so it no longer shows up in the error term. So I take it out of the error and I put it into a variable. And that's often how we do things. Same thing in serial correlation. I can add a lagged variable in the structural part of the model if things are correlated over time. So let's say I had, instead of having adjacent cities, that we had cities that I measured over several times. Well, they share unobserved effects. So I could add a lagged effect and say, well, let's use what happened last year when I observed the city as a variable in the model of what we call the lagged effect to pick up that correlation across the error terms. So it's usually these things are signals to us that there's... Now let me go back to the first comment. We are trying to capture all of the complexity. Remember one of the first statements I said, in the data generating process. These are complexities that are occurring in the real world that are showing up when we test assumptions and we're saying, oh, a minute, that's a problem for this particular model, so I need to adjust it to account for the complexity of the correlation across space or across time or endogeneity or truncation or censoring, all of these things. Because the real world isn't simple all the time. It has a lot of these complexities. And that's the art of modeling, is understanding the process enough to capture the complexity of the process we're trying to understand. Does that help? Okay. All right. All right, so maybe we just take a 5-minute break, just because we've gone for an hour, and then we'll jump into this next lecture. And just to refresh, would that be a good, yeah. Just to keep people fresh air and blood circulating and all that good stuff. Fairly quickly, predictor variables, right? Well, it is, I think it's always the case that the right-hand side, so types can be anything, Likert, binary, nominal, continuous, but often the left-hand side variable, the scale and the nature of the left-hand side variable determines, in many cases, the kind of model that we use. And dictates what we need to do to model it. So Poisson, or the count models, are a really, really good place to start to start this long discussion we're having around the complexity that arises in data and the real process, and why we need specific techniques to deal with specific situations. And count data models are just that. They're models that we use to model things that have a count outcome or dependent variable. Now this just doesn't really want to. So count data are fairly obvious and simple. They consist of integer values, non-negative, and they are usually a count. And there are a whole bunch of examples I'll show you up here. And so anything that can be counted or is a count qualifies as count data. We actually don't use, typically, linear regression to model count data. And there are a couple of reasons for this. They're properly modeled using a number of methods, but the most popular is, at least the starting point, is the Poisson and negative binomial regression models. There are other ones out there, but these are the most common, and they're a great place to start. So if we learn the basics of this, then we're in good shape. So just to show hands, how many people are familiar with count models? Okay, very few. So I will proceed on that basis. So let's consider the number of crashes occurring at a site, okay, at intersections in a city. So we'll use that as an example. And we can specify the model as the probability of an intersection I, which is the index for the intersection, having y sub I accidents per year. Okay? And the number of accidents is going to be non-negative, and it's going to be a count. We can't have 3.5 accidents. Okay? So we adopt a Poisson distribution. So a Poisson, anyone heard of a Poisson distribution? And how many dealt with a Poisson distribution in the last year? Okay. So I'm guessing that a lot of people remember Poisson from many years back. So Poisson is a count distribution. It's a distribution of integers. And we use the Poisson distribution as a way to describe what a distribution of counts looks like. Okay? And the model, it looks a little complicated, a little more complicated than what we saw for linear regression. Almost all models that we're going to look at are going to be a little more complicated than linear regression. But it doesn't matter. The functional form of the models that we'll look in the class, in all statistical models, some might be complicated, but the stochastic modeling process is the same. We're going to be looking for a set of variables, predictors, that influence the outcome. And this outcome are counts. Okay? So the terms in the model that you need to be aware of is this Poisson parameter lambda. Okay? So what we see here is that we have lambda sub I. So what this model says is that we're going to ask, lambda is the mean. Lambda is the Poisson mean. Okay? The mean of the distribution. And so because we have a subscript script I, what the model is going to do for us is it's going to predict the mean of the count at every intersection I. Okay? So if we observe a bunch of sites, it's going to say, the model is going to say, well, the average or the mean count at that site is predicted by this amount, and the mean one over there is this one. It's actually exactly what we did in linear regression. Linear regression predicts the mean response for whatever we're modeling. If we go back to the example of developing a population growth model, it's predicting the mean population growth for whatever spatial unit we were looking at. In that case, it was cities. So it is predicting the mean, but in that case, it's the mean of a normal distribution. In this case, it's the mean of a Poisson. So it's very similar. Okay? The interesting part about the Poisson distribution that we'll notice is that the mean and the variance are the same. So that is, the expected value of the mean, the expected value of y, is equal to lambda, which is equal to also the variance of y. So they have one parameter. That's all they need. Remember in the normal distribution, it has two parameters. It has a mean and a variance. and an infinite combination of those. So we're going to have a tight distribution, with a mean and a very small, or we're going to have the same mean and a really large distribution. But in Poisson, whatever the mean is determines the variance as well. Okay? So the most common relationship between explanatory variables in these models that we use is what we call the log, depending on what software you use, but it's the natural log relationship. So that lambda I is the exponent raised to the beta x. That's matrix form. So that's big beta x in matrix terms, because so it's beta naught plus beta 1 plus beta 2 times x2 plus beta 3 times x3, et cetera, et cetera, et cetera. Or alternatively, the natural log of lambda sub I is equal to beta x. So if you look at that second equation there, it's almost exactly like linear regression. In linear regression, we just had y, right, is equal to beta x. It's not that different. Now we have natural log of lambda sub I. So before we had y sub I, and so it's very similar. So the process of Poisson count modeling is not very different at all than regression modeling. Same thing, we have a vector of x's, variables that we think influence our count process, and we will use those to develop a model that we think is responsible for generating the data that we're interested in. The expected number of events per period is given by the expected value of y sub I is equal to lambda sub I, again, is equal to exponent raised to the beta x. We call that beta x a linear function of x, so or a linear combination of x's. For model estimation, we're going to use the likelihood, maximum likelihood estimation. So least squares doesn't work very well here. Least squares gives us biased on the properties of least squares estimation on the Poisson are not good. So we use maximum likelihood. That works because we have a distribution we've specified. If you remember, maximum likelihood requires us to have a distribution. We have one. It's a Poisson. So it's set up very well. So I'll walk you through that. So we have a likelihood function where we just have the likelihood of beta is equal to pi. The probability of all these individuals in the case of intersection sites, the probability that there's one crash at intersection 1, that there's 0 crashes, that there's 1 crashes, that there's 2 crashes, 3. So the Poisson distribution gives you probabilities of every integer outcome, right? So we would do that. So the bottom there is just the product of the probabilities across, in this case, all sites and all crash outcomes. And since lambda sub I is the exponent raised to the linear function of x's, we can substitute that back in, and we get the log function, or the likelihood function, for the Poisson model. Okay? Luckily, you don't have to worry about this. The software does all of this for us. I'm just showing it because that's for completeness. That's actually kind of messy to work with, so we take the log of it, and it becomes a nicer function because it's now additive, and computers can solve and maximize this easier than they can solve. It's actually humans that can program computers to solve this better than humans can program computers to solve the other equation. So that one turns out to be the one that we will get. So remember, just to refresh our mind, so the log likelihood function, what are we're looking for as the closer to 0, the better, and they're all negative numbers. So the closest negative number to 0 is the better the log likelihood. So if we estimate 2 models, and one's negative 100 and one's negative 50, the negative 50 is generally a better fitting model than the negative 100, right? Okay. So this is the first time I'm going to show you this, and this is something we'll use for the whole rest of the models. In fact, this goodness of fit measure is one that is used in so many different models that it's one that you could easily commit to memory. And it's the difference in log likelihood test, or the log likelihood ratio test. And this works as a general result. Almost all of the, whenever we have a log likelihood from a model, which is most models we'll deal with, this test is valid. And so the concept is this. And I'm going to walk you through this, and then I'm going to give you a general statement about statistical tests so that you understand them in general. So that this test basically says 2 times the difference in the log likelihood of some restricted model and some unrestricted model. So those are terms, restricted and unrestricted, just mean restricted usually means a smaller model, and unrestricted means a larger model, more variables to fewer variables. That's all it really means. You can compare any 2 models as long as they have different numbers of variables in them. And you're going to compare that difference is approximately chi-square distributed. Down here. So that statistic at the bottom is chi-square distributed with degrees of freedom equal to the difference in the number of coefficients in the restricted and unrestricted models. Okay? So I don't have a blackboard here, so I'm going to try to wave my hands through this. If you want to understand statistical tests, this is a statistical test. They're easy. They all work the same way. And I just want to give you a broad indication of that. This is the way they work. Some really smart statistician or econometrician has said this statistic, in this case, it's this. That statistic, if you do it over and over again, follows a really nice distribution. A distribution, in fact, that we know the shape of. And if we know that this statistic, if you do it over and over again, if you sampled over and over again and did it, and if we know exactly what the shape of that outcome would look like, we can start to say, assign probability to the outcomes. And to start to say, well, this difference, for example, in log likelihood, being a difference being this large happens 1 in 100. Right? So that's the kind of concept. So in this case, we're saying the difference in the log likelihood, how often does that happen? By chance. And if that difference happens so little by chance, then we're going to rule out chance as explaining the difference, and we're going to say the difference is because one of the models is significantly better than the other. That's how they all work. Every statistical test works on that principle, that we know how this thing behaves, some distribution. Because we know that, we can look at the likelihood or the probability of how it behaves, and we can start to say this is chance behavior versus not chance behavior. The difference is because of the model is actually better. And that's exactly what it does. So we then, if the chi-square probability is really low of achieving a difference that large, usually less than 5%, we say, chance can't explain it. The unrestricted model is significantly better than the restricted one. That test is going to come in handy a whole bunch for all kinds of models. So that's why I spent some time on it. So we have a pseudo R-square in these models that's computed as we call rho squared. So it's not, we don't give it an R squared because it's not exactly the same as an R squared. But it's rho squared, and it's equal to 1 minus the difference, or the ratio of log likelihood of the model with all of our parameters in it, divided by the log likelihood of 0 parameters in it, except for the slope intercept. So beta naught. So that's what rho squared is. So in a sense, what you're saying is, in a sense, conceptually, what we're saying is how much of the variation in the data how much more variation in the data are we explaining than just the slope-intercept term, or just an average, a flat line. So it's sort of the same as the r squared, which is how far away from the flat line are we? Well, the log likelihood of the 0 is sort of the flat line. It's just a model with an intercept in it. And so we're saying how much better is the regression function we've estimated. So it's the same concept. Perfect likelihood would have a model with a rho squared of 1, and a product across would also be 1. And the log likelihood would be 0, giving rho squared equal 1. All right, so that would be a perfect model. So you can see that. So if our model was log likelihood was 0, a perfect fit to the data would be 1 minus 0, and then you'd have a rho squared of 1. You'll never achieve that, by the way, but we want to get as close as possible. Okay? All right. So the Poisson model is very flexible. We can deal with truncation, and we can deal with censoring. Truncation is when we know data can't be measured above a certain limit, and censoring is when are discarded above a certain limit, and censoring is when they're collected, but the value is at a certain limit. And then remember, censoring is like how many people are on the bus. What's the demand for the bus? I can only measure the people on the bus. I can't account for the people waiting in line outside. So that's a censored variable. There's other kinds of censoring. We'll have examples in class in some of these other models as well. In fact, in our tutorial, we're going to have a censored variable we'll talk about. I might as well mention it now. So if I give you all a questionnaire and said, how many times, assuming we all work 5 days a week, okay, how many times in a week would you be willing to leave your house for work earlier than normal? And your answers would have to be between 0 and 5, right? So they'd be censored. Now, since it's an integer, since it's a count variable, we already know it's censored at 0 on the left-hand side. But on the right, we'd have to account for the fact that it's censored at 5, and that you can't provide a 6. Okay, and we'll see that in our example. So we can account for truncation. I'm not going to go through this in detail, and censoring. So there's some mathematics, some great, really smart statisticians have shown and done the math to figure out how to revise these models to deal with censoring and truncation. Thankfully for us. Now, it turns out that the assumption that the variance and the mean are equal is sometimes restrictive. And it may not be true in some cases. And when it's sufficiently untrue that, say, the variance becomes much larger than the mean, then then we violated the Poisson model. An assumption of the Poisson distribution is the equal mean and variance. So the negative binomial is only a model to explain the additional complexity that arises when the mean is actually smaller than the variance or larger than the variance. Okay? So again, we develop models to capture complexity in the real world and deal with situations when it doesn't behave like our models think they behave, or assume that they behave. That's a better way to say that. So often, not always, but often the case arises in civil engineering kinds of applications, transport, is that the variance is larger than the mean, the variance we observe. And so when the equality doesn't hold, we say that they're over-dispersed. We have cases of under-dispersion, but very rare. So we say usually they're over-dispersed, and we need to fit a negative binomial. The way we do that is quite simple, is that we add an extra term to the model. So we add that epsilon sub I. So we have the linear function plus some error term, where the exponent of epsilon I is gamma distributed with mean 1 and variance equal to alpha squared. If you look at this equation, this is the one that we should kind of focus on. The addition of the term allows the variance to differ from the mean. So if you look at the far right part of it after the equal sign, so we have the variance of y in this model is equal to the expected value of y, that's the Poisson, plus this additional term alpha times expected value of yi squared. If alpha is 0, then it collapses to the Poisson, right? That term goes away. So if alpha is, as alpha gets larger and larger, we see more and more over dispersion. So let me ask you intuition. Now, one of the things that, based on your past experience and what we're doing in this course, I find that developing a sense of intuition about these things is really important. So what does your intuition tell me about what statistical tests we would do to alpha? What would we want to test about alpha? What statistical test? Well, let me refresh your mind. So what statistical test do we do for our variables in the models? What are we testing for when we test them? It's a t-test. To test what? Whether they're equal to, yeah, right? We're testing whether they're equal to 0 or not. Whether we can rule out 0 as a possibility. So what would we test for alpha? No, what do we want to know about alpha? Yeah, same thing. It wasn't, so the trouble I run into is when I ask questions, often you think that's a trick question. And it's actually a very simple question. It's the same. We would want to know if alpha is 0 or not. Because if it's 0, then it goes away and we have the Poisson. So very useful test for us. And we hope, and it turns out that lim_dep gives us a test of whether alpha is 0 or not. Right? Makes sense? And it makes sense from this equation, because we want to know that. So alpha is referred to as the overdispersion parameter. The negative binomial distribution has been done for us by these really smart statisticians, but it looks like this. And it has a little more of a complicated likelihood function. Again, all of this is programmed by people like William Green to solve these functions for us. And we just worry about the practical, the subject matter. Right? So the people like William Green, brilliant people, but could care less really about safety at intersections and active travel and all that stuff. So we work in an area where we're focused on the subject matter, whereas people like William Green are focused on to help people like us make sense of the world. And thank goodness for people like William Green and other people that are focused on the methods and do this for, this kind of stuff for us. All right, now it gets further. It can get even more complicated. Not surprising, right? Life and the things that generate data can be complex. So there's another thing that can happen, and it's called zero inflation. And so when we observe events and counts, we can have a situation where in our outcome variable, in the integers, we have lots of zeros. And when we have lots of zeros, it's possible that we have a zero inflated process going on. But it's actually pretty easy to figure out if you do or you don't have that going on. But let's talk about what a zero inflated process is. So let me ask, I'll do a quick survey here. We have 10-pin bowling in India, right? Do you call it, what do you call it, 10-pin bowling or? Just bowling. Okay. In Australia, we call it 10-pin bowling. I don't know why. Is there a 9-pin bowling or 8-pin bowling? Anyway, so bowling. All right, so show of hands. How many people went bowling in the last month? That's all right. Okay, that's all right. Okay, getting the change. How many people went bowling in the last year? Okay, 3 people. All right, and I won't out. That's not a count. So that is I could count people, but if I did a survey and then I asked you how many times you went in the last year, let's say I did that, but you're the only 3 people that would have a positive integer count, right? You might be 1. Okay, let's add. How many times did you go in the last year? 2. 2. So there's an integer count. We have 2. 1. 1. So we have 2 1s, a 2, and a bunch of zeros. Right? Now, this is a classic zero-inflated problem. Because what you need to have for a zero-inflated problem is that there are a number of zeros here that people that would go bowling that happen to not go in the last year. There's a bunch of other people that will never go bowling. Effectively, what we would call zero-state people. I don't want to bowl. I'm not going to bowl. There's 200 things I'd rather do than go bowling. And unless I'd done all those 200, 199 in my day, then you can drag me to the bowling alley. Otherwise, I'm not going. So effectively, they're what we call a zero state. The problem is in our distribution of that survey or that information, we have 2 types of people or responses. We have the count people, the 2 and the 2 1s, and all the zeros who we just happen to not observe going in this last year, who would go, and all the zeros that would never go. So we call that zero inflation. We have a special model to deal with the situation where we know there are 2 types of zeros, true state zeros and the other type, right? And we call that zero inflated. And we can have zero inflated Poisson and zero inflated negative binomial models. So in the last 15 minutes, we've covered 4 different types of models for situations where counts arise and with different levels of complexity and underlying the generation of those data. The zero inflation, the thing I say about the zero inflation thing is you can have situations where we have lots of zeros, but it doesn't necessarily mean it's zero inflation. The zero inflation, to think that you have zero inflation, or to demonstrate or argue that you do, you have to be able to say qualitatively there are 2 different types of data generating processes that create zeros. And it could be people, but it could be other things. So, for example, at an intersection, could you have true zeros at an intersection? And actually, my most cited paper was a paper that argued that you couldn't. That was the whole purpose of the paper, that people were modeling using zero-inflated models for intersections. And a colleague of mine, Dominic Lord, and John Ivan, and I wrote a paper that said that doesn't make sense to use zero inflation for intersections because so much of crashes are random that you can't guarantee that a site is never going to generate crashes. And so you have to have a qualitative reason to explain why you have zeros. So then it raises the question, well, what if you have lots of zeros, but you don't have zero inflation? What do we do with that? Well, there are ways to deal with excess zeros that's not zero inflation. And it's just dealing with unobserved heterogeneity. And we'll talk about those a little bit later. You can deal with that in all kinds of different models. But so just because you have excess zeros doesn't mean you have zero inflation. Yes?
example,
Yeah.
example you gave about bowling.
Yeah.
So probably we can use 0 there, right?
Yes.
Because some people
Absolutely.
yeah. So it depends on the physical process.
Yes, exactly right. So it depends on the physical process. And this is another thing that, and I'm glad you raised that, because this is another argument to say you have to know your data. If you're just doing a mechanical process and modeling, you might find that a zero-inflated model fits data really well. But if you don't know what the process, the material explanation for why this is the right model or process, then you're just tinkering and playing with a model and not really understanding what you're trying to learn. And so it's very important, absolutely, that it's about a process. Yeah, yeah, yeah.
Okay. I'm actually working on one data where you have a long segment and most of the, we have taken a road, divided into small segments, and of course we are not going to see segments and accidents in most of the segments. So in those cases, when you actually it did not happen only by chance. Of course, it could have happened.
Yes.
It just did not happen.
Right.
Given the time frame I'm looking at, or given the data, maybe some data was missing. So in that case, can I actually call that a zero-inflated model?
I would suggest no. You can't. I would suggest that you deal with it another way.
Will you be teaching us how to deal
Yeah, no, but I can. I can talk to you. I can talk to you about that. Yeah, how we can do that. Yeah.
And also just to add, like what you are doing, the way you are collecting data, you are generating a lot of zeros. You are
Right.
segmenting it.
Yes.
So it's not a zero.
Okay. There was another
So
question.
on the same line, it can't be used in its case, but why should we use in the example that you showed, that number of people who went for bowling?
Yeah. Because qualitatively, what you can argue is that there are people that will never bowl, that will always be zeros. And then there are people that will bowl, engage in the activity. And so you have two different types, qualitatively types of people that generate zeros. People that just won't bowl. And so no matter when I observe them and ask them a question, they're going to give me a 0. And then those that just happen, that have positive counts, the 3 people in this classroom, and any other people that, so for example, if I ask the question in the last 5 years, we might have a couple of other hands go up. All right, so those other couple hands might have been the people that are bowlers, but just didn't go in the last year. So we're zeros, happen to be observed as zeros. But the rest beyond that might be true zeros. So you have qualitatively 2 different types of entities generating the data. And that's why you have so many zeros. And if you, so so as we go, I'll show you the model. As we show you the models, I'll show you how it works, okay? And then it'll give you some more clarity about how the zero-inflated models work. We'll spend some time in this tutorial looking at zero-inflated models. We'll do it knowingly that it may not be a zero-inflated process. We may not be able to justify a zero-inflated process, but we'll do it just to illustrate what this process looks like. And I will purposely look at how we deal with the excess zeros without using a zero-inflated process, so you can understand that. Yeah.
You said that in this bowling case, the people who won't go for bowling, so basically there is no probability associated with them because they are not, they won't go. But in accident case, you can't say that since there has been no accident, there is no probability of being accident.
Yes, that's right.
Zero model in this case, since no probability is associated with people who are not going.
Okay, so let me I'll explain it now and then we'll show you in the tutorial. The way the zero-inflated works is it says, it's actually 2 models. And the one model says, let's try to predict how many people are true zeros versus not true zeros, versus people that count process data. So and it actually assigns a probability that someone's a true zero and a probability that they're not. So, and then for the count process, it predicts a model of those that would generate a count, including zeros. And so it splits the model that way, so in 2 different things. So it would say then there's a group of sites that have very low probability or high probability of being true zeros. It doesn't mean for certain they're true zeros, because it's a probabilistic model. So it just says these are high probability of being true zeros. These are low probability of being true zeros, and you would actually generate a count. And so that's how it works. But I'll show you. We'll show you how that works in the tutorial. So it's very clear. Okay. Yes. Question.
So, can we use these models for interpreting the latent demand?
Interpreting latent demand. Can you give me more detail there?
See, the people who do, I mean, I will concentrate more on pedestrians. The people
Yep.
who don't walk, maybe because they don't get the correct infrastructure, so that is particularly zero. And there would be a kind of people who would walk if there is a there is a proper infrastructure on roads.
Yes.
So,
So I haven't thought about that application before, but that's a really clever application of a zero-inflated model. That is, you'd be really interested in knowing and predicting how many true zeros there were because they have constraints from infrastructure, and that they can't walk or they can't fulfill, is in this case pedestrian, they can't walk because they don't have, they're either too far away or they don't have the infrastructure to feel safe enough to walk, so they're effectively true zeros. And that actually becomes a really important part of what you'd be interested in the model, because you're trying to say, because of the infrastructure, there's a whole big proportion of, we estimate there's this many people out of 100 participants, potential pedestrians, 80% of them are true zero walkers because of the infrastructure. That's a very interesting application. So yeah, I think you could do something like that. Yeah. Yeah.
For simulated model, what percentage of data points should be zero? Is there any percent?
Okay.
50% of the data point is zero?
Okay. So it's a good question. So the zero inflated. So the question is, what percentage should be zero? It actually, there isn't a magic percentage, but the way it works is that, so if you have a low Poisson mean, then you're going to have a lot of zeros anyway. So the zeros thing only comes up to say that it only raises its head of having excess zeros if you have more zeros than explained by the Poisson mean, the estimated Poisson mean. So if you have a large mean, you can take a random number generator and say, draw 100 observations from a distribution with a Poisson mean of 10. You probably get very, very small number of zeros. So the percentage of zeros would be very low. So let's say you got 2 zeros. Well, if you had 10 zeros, that's potentially zero inflated. You have more zeros than explained by that Poisson mean. But if you had a Poisson mean of 2, you might have 80% zeros, 70% zeros. And so then you'd need 90% zeros to have then zero inflation in that case. So it really depends on the Poisson mean and the count, the observed counts to know how many excess zeros you have. So it's only a trigger if you have more zeros than explained by the observed counts. So conceptually, in this example, we had a 2 and 2 1s. So if we calculated the mean for that, it's going to be very low, right, from that. And then we would say, well, how many zeros would be expected with that kind of mean? Well, it's probably not as many as in the room, right? So that's how it would work, conceptually. Yeah, question. I'm glad you all have good questions about this. It's clearly an interesting model for a lot of you. Yes.
In my research, there are some binary variables which will change when I'm doing it longitudinal, like the ownership of an airport.
Yes.
But if I'm talking about is it an island airport or not, that won't change in a longitudinal study. Is it related to when we're dealing with binary variables, one and
no, not necessarily, but I think we can deal with your situation in different ways. So you were talking about changing x part way through the observation period. Is that right? Yeah. So a different situation, but I'm not seeing the connection to the zero inflation from what you described there.
So that's not a count.
Yeah. 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 So I'll plant that here, and we'll try to come back to that when we go to the discrete choice, which could be, you know, or a different kind of model, or we talk offline. Either way, I want to understand what your issue is there a little better. Yeah.
For the negative binomial model, in a particular case, I am not getting the distortion parameter as a significant factor. So in that case, can I go for Poisson model, even though the variance is higher than mean?
Yeah. So that's exactly right. So and we're going to go through the tutorial. We'll do the work with data. But the concept is so in reality in sampling, we're not going to get a mean exactly equal to the variance. So the question is, when, and just like the statistical test, when is the difference between the mean and the variance so large that chance sampling can't explain it? And so we'll do a test to say the mean and the variance. We'll test whether they're the same. And we'll want to rule out chance as explaining the difference. And when we say, oh, there's less than a 5% chance of having a difference this large between the mean and the variance, then I need to use the negative binomial. And if you can't rule out zero, then chance explains the variation that you have. And so you say under a Poisson process. So it says if I sample from a Poisson process, by chance alone I'll have that much variation in the mean and the variance. So that's acceptable. So that's really the notion. That goes back to that statistical test, is how they all work on that basis, is that we're just looking at the chance of having observed a difference that large. So yeah, you just collapse it to the Poisson. And it's a good question, because why would we use, and this is that big discussion about would we want to have more complexity when it's actually less complex. We don't want to have more complexity than necessary to explain. The negative binomial is more complex. It's another parameter. It's an alpha. And the alpha may be too complex than for what we actually have. So we wouldn't do it. We want it as simple as possible, explain as much complexity as we can with as simple as a model as we can. So, and that's why we have these statistical tests to ask those questions. Is it worth having alpha to explain the complexity? Is it worth having a zero inflated process to explain the complexity? Yeah?
The significance level of alpha, is it depends on the sample size?
Yes.
It depends on the sample.
The significance of any statistical test always depends on the sample size, no matter what we're doing. Always, always, always. Yep. So yes. Yep. Okay. We're ready to keep going? I love the questions. That's absolutely the best way to go through this. Okay. So I've really said this, the zero inflated can be, it's really a qualitative distinction, and you've got that in your notes. All right. So there's the form of the zero inflated model. It assumes that there's two different processes going on, a count process and the zero inflation process. And normally what we do is estimate a binary logit model as well as a count Poisson regression. So we do sort of a two-stage model. So that's the bottom. So the splitting process usually is assumed to follow a logistic or probit normal probability process. And those are the two common ones. So there must be an underlying justification for this. You need to be able to remember the 5 things of causality. That first one was a material explanation. and this is coming back to you, I'm hoping this is coming back to you, you need to be able to stand up and say, this is why we have a two dual state process. These intersections or these households do this, these households do this. These households can't walk because they don't have the infrastructure, so effectively they're true zeros. Brilliant concept that we could model it that way, and we're trying to capture the true zeros. Does it mean they're always a true zero? No. In this case, we're trying to convert them away from being a true zero, and that's part of the argument to say this is what our estimate is. I mean, how cool would that be to estimate in a before case and estimate the number of true zeros, do an intervention, and then estimate what's happening after and see the number of true zeros has gone down. I mean, that would be a really great study and evidence to suggest that your intervention was successful. As well as more people engaged on the count as well. So the count side also showing more people engaged in walking and activities. Really great example. Okay, so the appropriate, almost always, when we propose to do something more complex, there's a test to see whether it's worth it. And so in this case, it's Vaughn came up with, another smart statistician came up with a test that said we can test to see whether this zero inflated model is worth it. Same principle. This statistic is approximately chi-square distributed. I think it's chi-square. And if you calculated that statistic on numerous samples, we know how it's distributed. Therefore, we can talk about how likely it is that the zero inflated model is significantly better than the other model by chance alone, right? And so we do that with all of these kinds of tests. And the Vaughn statistic, so that's the statistic that he calculated. And the LIMDEP gives us the Vaughn statistic. We're looking to reject the null hypothesis that the non-zero inflated model is sufficient. So we're looking for such an improvement in the model from using zero inflation that it can't be the improvement can't be explained by chance alone, right? Okay, so Vaughn is asymptotically standard normal, so it's actually not chi-square, it's normal distributed, all right? And so really smart guy showed that statistic is normally distributed with certain properties. And so we can look at the critical value of the Vaughn statistic and to provide the statistical evidence for a zero inflated model, which is not sufficient to argue for that model. We need the material explanation to go with it. Okay, so large values of V greater than the critical value of V favor model 1 over model 2, whereas large negative values support model 2. So, so there's the decision criteria for the Vaughn statistic, and you can see that what we have are 4 different models to choose from: negative binomial, Poisson, zero inflated Poisson, and zero inflated negative binomial. And so we have tests to help us decide: do we have over dispersion or not? Do we have zero inflation or not? Depending on the results of these tests, we can then provide the statistical evidence in support of increasing the complexity of the process. Okay, so this is your question about, or was your question about the excess zeros and the over dispersion? I think it was yours. So we don't have to always use zero inflation. It can arise from other processes, too many zeros. So we can use what we call unobserved heterogeneity to capture excess zeros. And that's that bottom point there. Okay, so for example, in your example, just the size of the units themselves may be contributing to the excess zeros. It's not a zero inflation process, but it's just the nature of the definition of units. So we can use a different unobserved heterogeneity to capture that. So what on earth does the word or the phrase unobserved heterogeneity mean? My gosh, what a complicated word or phrase that is. What does that mean? I want us to know what these words mean. So when I throw them around, you say, well, I understand. You use the phrase, but I don't really know what it means. But I want you to know what it means. What would unobserved heterogeneity mean? So you're right, absolutely right. So look, it's important when we go through and learn statistics and modeling that the terms that we use make sense to us and we can put them in concrete terms. So it's unobserved, means that there's some factor that we didn't measure. It's not one of our x's. So it's something out there, some attribute that we don't know. And it's heterogeneous or heterogeneous. Heterogeneity means that it's increasing variance in the data. Increasing variance of something that's a Poisson process would be adding zeros. It's going to increase the variance. 0 is the bottom number. It's the lowest you can observe. So it's going to increase the variance. So it's something unobserved, like how we selected the units, which is not an x, and it's adding to the variance. So that's what it is. But it could be other things. It could be an unobserved variable that we didn't include in the model. Okay, so that is the end of the lecture. We are ready now to jump into the tutorial. So what do we have till noon in the class? Is that what we have? Okay, so we have plenty of time, so we'll get through this tutorial. Now, computers, did we, well, do we want to move to the lab? Take a break and move to the lab? I'd really like to get everyone working on computers.
What I understand that you do not have the laptops, right? So our plugging is an issue, right? So maybe we can move to that lab.
Okay. Yep. All right. So it sounds like we're about to move. Are there any final questions to wrap up this? We're about to leave because we do have more time, and I'll answer your questions. Yes? What's the difference between normal and gamma? That's a hard question to answer. I mean, it's no different than what's the difference between a normal and a Poisson. In what? So the gamma is used for. So you're saying that you're using a gamma for? You're talking about the gamma for the distribution of the alpha, right? Yeah. So let me explain that the best I can. Sometimes, and you'll see this in the Bayesian models that we do and some of the other models that we look at. Sometimes we choose actually we'll see it in the discrete choice. We choose, or statisticians have chosen distributions not because they fit the process super well, but because analytically they're very convenient. And they fit the data or the process we're looking at fairly well. And the gamma is a perfect example of that. But there are going to be other examples that we come across. So it turns out that the gamma with mixed, as a distribution for alpha, mixed with the Poisson is what gives rise to the negative binomial. If you didn't use the gamma, you wouldn't get a negative binomial. Because analytically, the combination of those two and the way they're specified gives rise to the negative binomial. And the negative binomial is a known distribution. And with known properties, so we like that. Statisticians like that. If we use something else with the Poisson, we might come up with a brand new distribution that would have to define parameters for and tables for, and that becomes cumbersome and difficult. So we use analytically convenient distributions often to make the math work out, be solvable, parameters to be estimable, and all those sorts of things in lots of cases. So that's the first case we've seen. But in discrete choice, we do it as well. And a lot of other models, we do it as well. And because it's convenient. And it's often fairly reasonable assumption as well. But anyway, I hope, does that answer your question? Yeah. Okay. Any other questions before we? So now, do people have to go elsewhere to get their laptops, or what? How does that work? Is everyone able to just go transfer over to the lab, and then, I mean, should we just meet there like in a half an hour, or? Yeah. Okay. The lecture. Yeah. No. We'll just do the lecture. Yeah.
The plan was 2 lectures, then 2 tutorials, and then 1 lecture. So the 2 lectures are over. The 2 tutorials will be doing in the seminar room of Civil Engineering Department. Then we will break for lunch, and then 4 o'clock we will come here. 4 to 6 will be the lecture. Okay? Using LIMDEP rather than using some SPSS.
Oh yeah.
There are some other software packages.
Oh yeah.
SPSS, like suppose in LIMDEP also.
So I don't know SPSS very well. Stata. I don't recommend SPSS. Stata I do. But SPSS does do it.
We don't know that much, but many times I used SPSS for some basic small modeling.
So SPSS is more of is developed more by social scientists, and so it's lacking some of the more econometric kind of things, whereas Stata is more of an econometric package. So Stata would be the one I'd recommend outside of LIMDEP. That'd be my suggestion.
In limdep also we don't have any, like, if I click to get, here you are using command lines.
No, there are the pull down menus. I'll show today in tutorial. I'll show that. There are pull downs. Yeah.
আজকে বলো না কালকে আর পরশু
Yes, that was your. Did you try it? Yeah. Yes. Yes.
Then I made this variable into normalization.
Yep.
This is x1 minus x2
Yep.
standard deviation, and this is a raw basic sample
Yep.
of the x1, and this is a normalized version of the x2.
Yep.
Then for the modeling purpose, I need to consider these values as normalization.
No, just the normalized.
Only for the normalized.
Yeah.
Not value.
No, in the model, you're replacing the model. You're replacing the original x with the standardized x. You're getting rid of it.
If I considering both the variables, if I in my model, if I want both the variables, then I'm converting the x to all those values into normalized values.
Yes.
And in the final modeling, should I consider all those x1 values and all the normalized values of the x2?
So you can try just normalizing one of them and then using the normalized. But if the correlation is still high, then you can normalize them both. So I just tried one
First,
first.
initially I need to check the values of the x1 and the normalized, the correlation between these two values.
Yeah.
If it is less than something, my standard value is 0.5 or 0.4, then both are considered.
Yeah. But so yeah, but you get exactly. But when you transform it or standardize it, you're using the new one in the model, not the old one. Yeah. Because there's no information loss at all. It's all the information is still there.
I'll try then.
Yeah, I'll be very curious to know what happens there. I'd be
এই জলটা
curious
কি
to hear
ওরকম
the
নাকি
result.
জানি না।
Yeah. So you what are